Hello everyone, I am Aditya and this is our first lecture on the journey of mathematics part 1, and today we are starting with basic properties of number, and it is our the first lecture. So let's start with natural numbers and their algebraic properties. So we are starting with natural numbers and their algebraic property, and the first topic in this is set terminology. So the natural question is that what does it mean by set? A set is a collection of objects. So the next question arises that what types of objects we are dealing with. In mathematics, we deal with the objects that are well defined. And what does it mean by well defined? A property is said to be well defined it for the given object. The property can determine to be either true or false, no, but not simultaneously. So in when we deal with set, we are about to concern on the property that are either true or false, not whole simultaneously. That like we have to just construct the sets of any five famous peoples. So maybe that I may make a set that is totally different from your perspective, because for my understanding of seeing people may be different from yours, so it depends on the personalities. So but when we when we ask the question like, let's suppose we have to construct a set of five natural number that are divisible by 3, or five consecutive prime numbers, set of five consecutive prime numbers, will then the sets are defined to all. That does mean that it is well defined. So the next question is that if we have property, can we form a set from it? The answer is no. We cannot form a set solely from arbitrary property with reference to the pre-existing collections. This issue we'll study in detail in set theory and related to the famous Russell paradox. We will cover this in when we study about axiom of comprehension. Axiom of comprehension means that we have a property and we can make any set from that property. That's called axiom of comprehension. But this results in the Russell paradox, like self-contradicting self-contradicting, or we can say that self-referential paradoxes. So to avoid that thing, we restricted our axiom of comprehension, and that is called restricted axioms of comprehension, or we can say axiom of separation. Now move to the another thing, representation of sets. So we denote the set by capital letter and their elements by lowercase letter. We represent set by capital letter and their representation by lowercase letter. This means that small x is element of capital A of the set capital X, where the symbol this denotes belongs to. So we can write that small x belongs to capital X. There are two common ways to represent a set. Roster method. In this representation, we list all elements of the set in curly braces and separate them by commas. So as earlier I have mentioned an example, we have to form a set of five consecutive prime numbers. So we can write five consecutive prime number, 2, 3, 5, 7, 11, and then we make brackets, curly brackets, and then separate each of them by comma. So that is called roster method. Now move to the set builder method. So in set builder method, we just need to describe the set with their properties. We don't have to write its elements. Let's say like I have to write set of 5 consecutive natural numbers, so we can write that x such that x is prime. We can say that x is prime, or it is this is prime, and it is, let's say that there are 5 consecutive primes. We can say directly like that. We can write the properties of the sets. Okay, now move to these things. Now move to another equal sets. And two sets are equal if and only if they contain exactly the same elements. Like how you have any two set 1, 2, 3, and you have another set 2, 5, 7. Since it doesn't contain, since each elements are not belongs to same, not equal to each other, so we cannot say that these two sets are equal. And if they are equal, it means that they contain exactly the same elements on in A and B also. So now move to the subsets. A subset is a set A is a subset of set B, denoted by this, if and only if every element of A is also in the element of B. So let's say I have take an example 1, 2, 3. Now we have to construct a subset from this set. So we can take any element 1, 2, and since every element of this set belongs to this set, so we can say that this set is subset of this set. Let's say this is A, this is B, so we can say that B is subset of A. And another point to be noticed that every non-empty set, it means it has no element, is a subset of all set. So there is another definition is also that what is proper set. What is proper subset? A proper subset of B, A is proper subset of B if A is subset of B and A does not belongs to B. Simply like that. So there is another extra condition that A should not be equal to B. We can say that A is proper subset of B, and we can write is that A is proper subset of B. Yeah. So now we have done the part first. So now move to the natural question. That what is natural number? Although it is difficult to define what a natural number is, we intuitively say that it meant for counting. We actually do not need to define natural numbers. As we see their properties, we will become familiar with them. So quickly let's come to the notation. We note the set of natural number by this. That is a set of natural number. So now we are defining the properties on the set of natural numbers. So addition. If we have two finite set whose cardinalities of m and n, then addition is intended to represent the process of combining these quantities. Yeah, but we are not dealing with such kind of things. Because in set, that this representation is same like that, because in set order doesn't matter. Order does not matter. So when we will deal set, we need to know that the order of the set does not matter. It means that it represents, if the elements are repetitive, we can write simply like that. So why we are not defining addition as through cardinalities? Because there is one reason, is that order does not matter. The sets are unordered, we can say that. And second, that is that we will, when we will see in combinatorics, that there's, when we combine sets, they somehow we have to include something and something to exclude, that we will discuss in pigeonhole principle. So we are not defining set, we are not defining addition as a through cardinalities. We are defining, to define addition intuitively, we need to understand what natural number represents. So we will have to understand what natural number represents. So 1 is denoted by this. Let's say this is simple. So we can write, it represents the 1 is in the large circle, we can say this closed curve, and 2 is denoted by 2 bar, 3 is denoted by 3 bar, and so on. And if n is natural number, the successor of n is n plus 1, and it is simple. Like we have to find the successor of, let's say, 5. So what's the successor of 5? We have 1, we have 5 sticks, 1 2 3 4 5, and we have to just, for successor of 6 we have, sorry, successor of 5, we have to just add one more sticks. Yeah, so this represent 5 plus 1, that is written here. So successor is denoted by this, and representation of addition as this, by this symbol. Now there is another observation, we can replace every natural number with these such kind of intuitive diagrams. So now we have to add two things. To add two elements of n, we pick two elements and draw a larger circle, close curve around them, and then we open individual curves of the elements being added inside the larger close curve. Let's say we have to add 2 plus 3, so we can write 2 as this, 3 as 3, and then we mix a large circle. Then we make a large circle, and then we remove the individuals curve, so we get 1 2 3 4 5, that is 5, and that is written here. So we can say that you have 2 sticks, you have to add 3, you can just draw 3 sticks more and simply add them and simply count them again, you can get the answer. So now move to the another section, that is carrying in addition. The main idea of carrying is that we are dealing with the decimal base. It means that everything is written, every numbers we are dealing in the form of base 10s. Let's say, what does it mean by bases? You have number, let's say we have written 234. It means that, okay, just see, this is ones place, this is tens place, this is 100, this is hundreds place. So now you have to write this like that. So this is representation is called expandation of numbers. So we have expanded this in the base 10. You have any numbers, let's say you have AI belongs to 0, 1, 2 up to 9. So this is unit digits. So you can make a numbers en minus 1, en minus 2, like 2 up to a naught, that is equals to a n 10 score 10 to the power n plus a n minus 1 temple a n minus 1 10 to the power n minus 1 n minus 1 plus to so on up to a naught. Here we can see that thing, it is written. Yeah, this is same thing. So the main idea of carrying is that we have to deal with the places. So like say, when the numbers of unit digits inside a collection become large, we introduce a rule of regrouping. And when we deal with the units on units then hundreds place, we can say that the idea of calculating and understanding numbers become easier, because you don't have to repeat, we don't have to know what comes next. You can simply build any number using these things. Okay, there are so many bases, so just we are dealing with decimal. So this is the expansion of decimal representations. Idea of carrying, suppose we add two numbers whose total number of unit exceed 9. The rule is group into bundle of 10 and replace 10 unit by one bundle, and remaining units stay as the same. So we are just, let's suppose we have to add this. So when we have to add, we have to add 8 plus 7. So what we will do, that we have to, either we can write everything, we have to just make 8 bars and then write 7 bars, and then we can just calculate. So now there is another approach too, we can just make a bundle of this 8 plus 2 plus 5. We can say this is 10 plus 5, that is 15. So that's simple. Now move to the another things, that's carrying as structural operations. Let two natural numbers be written in base 10 form. So this is written in base 10 form. We have to perform component voice addition. Let's say 325 to add 2, 8, 289. So that is 9 5 14, carry 1, 2 1 3 8 3 11, carry 1, that is 3 2 5 3 1 4 4 2 6, that is 6 1 4 when we add these things. So we are adding component wise and it is shown here. So when we get an extra places, we just replace to the next one. So carrying is not an additional operation. Yeah, carrying is not an additional operation. Yeah, it is true, because we don't, because addition is simply to know what's the total is. And when we deal about carrying, it depends on the basis. When we will discuss about binary representation, we will see that its carrying over is different from this. Yeah, both have same understanding. So thus addition is fundamentally concentration, concatenation of units, and regrouping by powers of 10. Now move to the conceptual summary. Addition consists of two steps: combines all units, disjoints units collections, and hierarchical comparisons, as we have discussed, like in vertical addition. Multiplication. What does it mean by multiplication? Addition combines units into single collection. Multiplication describes a more structural process, repeated with spatial organizations. It is a collection of units. Addition is collection of units, and multiplication is arrangement of collection into a grid. Let's say you have to arrange 3 dots into 4 places. Sorry, there are 3 dots and there is another 3 dots. Four places, 3 dots, and we have to just calculate how many dots are there. So we can, how to do this? Just see. Here we are writing 3 dots into 4 groups, or we can say that 4 dots into 3 groups, and so there are 12. This is repeated, is like that. Group of 3 dots, chunks of 3 dots into 4 groups, and either we can say that chunks of 4 dots into 3 groups, you will get this thing, same like that. So you have to add identical groups of 3 units. Geometric interpretation or rectangular arrangement we have seen in this. So another one of things to note is that when we deal with addition, it is simply forming the first 1D lattice, and when we deal with multiplication, you are getting 2-dimensional sheet. 2-dimensional sheet. So A times number of points in AB rectangle. This is clear from this. Now structure meaning multiplication is not just repeated addition, it represents two-dimensional organization of units as we have seen. The formation of rectangle from linear collections. You have this collection, linear collections, and you can just make other collection and get you form a rectangle. Encoding interaction between two quantities. Yeah, as we see that it is more about comparing things to, like when we study ratio proportion, it's quite familiar with these things. Distributive structure. Multiplication interact with addition via distributions. This is the fundamental properties to remember that thing. And let's say interpretation, a rectangle of structure BC can split into two rectangles. This, let's say you have this is, let's say this is a, wait a minute, I have to delete these things. Let's say this is A, this is B, this is C. Either you have to find the area of this triangle, this rectangle. So this is A times B, this is A times C. Either you can write like this or you can write like this, A times B plus C, both are same. That is written. Carrying analogy in multiplication, just as addition requires regrouping of 10 units, multiplication produces larger immediate bundles. When multiplying multi-digit numbers, we compute partial rectangular blocks and then regroup using base 10 structure. See how we are doing the things. You are just writing that we are expanding these things into the bunch of group of 10, you can say that, and then you are expanding it with distributive properties, and you get that things. Let's say you have to multiply 23 times 59. So what will you do? That when you multiply this, you just say that 5 9 3s are 27. That is, so we have to just add three chunks of 3 dots 9 times. Okay, 9 3 is 27, and that's the when since 27 we have to carry 2 here. So 9 2s are 18, 18 to 20. Now let's see what this happens. You have 50 plus 9, and that is 20 plus 3. You have multiply by this, so now you have to multiply by 50, not 5. So you can write here that when we multiply by 50, that is 0, and then we 5 3s are 15, carry 1, 5 2s are 10, 10 1 11. Now simply you have to add this 0, sorry, this is 7, this is 5, this is 3, this is 1. So that's his multiplication. Multiplication is repeated addition, linear way, rectangular formation, geometric way, and bilinear combination of structure, algebraic way. Algebraic properties of natural number. Now comes to the algebraic properties of natural number. After defining natural number, addition and multiplication, we now study the rules governing how these operation behaves. These rules are not arbitrary. These arises from the way numbers are constructed as collection of units and structural arrangement. Closure property. For all natural number, for all a and b belongs to natural number, a plus b belongs to this. That's represent for all. That represent for all. So this holds in this too. So that is closure property. Combining collection of units or formation of rectangle arrangement never produces something outside the system of natural number. Simple. Now move to the commutative property. It means that order doesn't matter. How you add two quantities, it remains same, and how you multiply this, it's same. Okay, merging two collection does not depends on an order, and same thing. Now move to the associative property. Associative property is that thing. How you where to take brackets, it doesn't matter. That's the grouping of unit does not affect the total collection. Same thing. Grouping of rectangle constructor doesn't change the final arrangement size. Distributive property, that's we have discussed. Now there is another existence of identity element. For this is called a0 is called additive identity, and one is called multiplicative identity. Identity. Yeah, that's now interpretation. Zero empty collection contributes nothing to the union. Multiplication by 0. Now let's prove this thing. What does it mean by multiplication by 0? So you have elements, let's say you have to a b minus b, that's b minus b, it means that it is 0. So ab minus ab, that is 0. This is 8 equal to a times 0, that is equal to this. Now move to the order property. Law of dichotomy and compatibility. Law of dichotomy, what does law of dichotomy say? That if you have any two numbers, natural number, so then either both are same and either one of them is greater than or less than of with others. So now we have compatibility with operation. If a is less than b, then a plus c is less than b plus c for all natural number. This simply for multiplication. Now structural summary. The natural number form a system satisfying this closure, that is closure, symmetry, commutativity, and consistency of grouping, associativity, distributive interaction between operation, and existence of identity element. So we can say that these properties include the fact that arithmetic is fundamentally a structure manipulation of finite collection of units. Now move to another thing. What is exponentiation? So exponentiation is repeated multiplication. What is exponentiation? Addition combines units in the line of structure. Multiplication organizes units into rectangle. And exponentiation extend this idea. It builds stack of rectangular living forming three-dimensional structure, or maybe say you can say four-dimensional structure. That depends on. So it is repeated multiplication. When you have to multiply 2 times 2 times 2, you can simply write that 2 3, 2 to the power 3. Now move to geometrical interpretation and stacking of grids. So let's say this is called exponent. Exponent. This is whole called power. And this is called base. So here a to the power n, we can say that this is base, this is exponent, and this total is called power. That's the terminology. Now move to the geometrical interpretation and stacking it. Yeah, it's simply denotes that things. You have to read stacking. When you have to mix three structure, you have to stack grid of 2D, and you will form the 3D structures. Structural meaning: exponential represent repeated multiplications, and this is and growth of dimensionally hierarchy. So these things we have covered this. Now move to the special cases. So this is the special case, and this e to the power 0 is equal to 1. Collapse to empty stacking level. Now, as you know that for now I can't prove that thing, that how it is 1, how it is 1. But when we study the law of exponent, we will able to prove these things. For now, just use it as it is. Or you can just simply say that what does it mean by, I'm trying to give you the understanding. What does a1 represents? That is a. So when you have to remove this, so what does a naught represent? A naught represent is a times a. How can I say that? Let's see. A square represent a times a. A1 represent a times a by a. So you are just excluding one a from that thing. So in that way you get this is equal to 1. Exponentiation is operation of hierarchical growth. A to the power n is iterated multiplication forming stacked geometric structure. It represent the transition from area volume to higher dimension scaling. Law of exponent. This is simple. When you have to now, just let's say you have to add this thing, multiply these things, that is a m times, and that is this is n times. So you have to just multiply this. You can write it like that. You can multiply total, you get a to the power m plus n, or you can just simply write it that a to the power m times a to the power n power. Simply simple is that, let's say you have written this a to the power m, a to the power m into a to the power n, that is n times. So you can write like this, simple. Or either you can do it like that, either you can also also write everything into a times m. So this a times m, and all these things, the m comes into n times. So you can say that a to the power m to n. So total is mn. Total we can get mn. And third is this. You can prove by on. It's not hard. Structure meaning of exponent law. Exponentiation obeys these law because it is repeated multiplication, hierarchical stacking of structural hierarchical stacking of identical structures, counting of identical layers. The exponents laws are not separate rules, they are consequence of counting stacks. Logarithm is just opposite of exponentiation. So I'm just moving to this point. This is called logarithm. So what does it mean by logarithm? Let's focus on that thing. Okay, you have a to the power x is equal to n. It means that, what does logarithm say? Logarithm, it means that you have to find logarithm of n with the base a represent the exponent. That's it. That's the meaning of logarithm. Logarithm is not new operation. Counting of that stacking, depth of stacking is reverse. You have to find the, it means you have to just find what's the exponent, is it? Yeah, when you have n is written in the power of a, you have to find what's the exponent of this. That's logarithm represents. So now move to the factorial. What does it by factorial? After studying exponentiation, stacking, repeated identical structure, we now consider different type of growth. Instead of repeating same objects, we consider arrangement of distinct objects. Now we have to for arrange distinct objects like that. We have to, there are 5 places. You have to arrange 5 distinct objects. So you can say that this has 5 choices, this has 4 choices, this has 3 choices, this has true, this has 1 choices, and that is 5 factorials. That is multiplication. So that represents this. Okay, now move to factorial. Counts the number of ways to arrange n distinct objects. Let n be the representation, n object be represented by this, then factorial counts all possible order configuration of these objects. Now move to the another thing. We build permutation step by step. So we have done these things. Positions, choices, how many choices are there. Geometric interpretation, arrangement layers. Factorial can be represented as layered selection process. At each step, we choose one element from shrinking set. Each choices create branching structure. This form tree of depth n with decreasing branching factors. So what does it mean by, let's see. Okay, so what does it mean by that? Each step we choose one element from shrinking set. As we have discussed this example of arrangement, we have seen that this has 5 choices, this has 4 choices, this has 3 choices. As we keep going, the choices decreases. That means the selections decreases too. So it means that we are dealing with shrinking set. The set is shrinking, and each choice creates branching structure. Yeah, it's mix the correlation between the upcoming elements or arrangements, so we can say that it is branching structures. So now move to that examples. All permutations are this from in this sets. So that's simple. Now relationship with previous structure. Factorial differ from earlier operations. Addition combine units, multiplication identical groups, exponential stack identical layers, and factorial represent direct distinct element. Permutes distinct elements. Structural meaning. Factorial represents growth of order complexity in finite system. Okay, it means simply that how we arrange things. Order, it simply means arrangement. It measures how many structures can be organized rather than how large it becomes. Summary. That's purely finite combinatorial quantities arising from sequential choices and arrangements. So this is all for today. In the next section or next lecture, we will study subtraction and integer as well as fractions. So thank you for watching this. Have a great day.